Alright, we're going to go in here and try to find some uses for real life inverses of quadratic models. So the learning target is I can write the inverse of a quadratic model to evaluate a real life situation. Alright. And there are times that quadratics are very functional, specifically having to do with gravity, for one. And here's something you need to know, right? If we're working with real-world applications, I don't know if you remember us talking about it when we did inverses, right? If I was going to switch two values, you know how we just switch our x and y, but in real-world situations, I can't just switch, like, in this case, time and distance, because just the fact that I change the variables doesn't really turn time into distance, nor does it turn distance into the time. So what we end up doing is we just solve, right, for the other variable. So where you might start off with, right, it's more useful to use the notion x of y rather than y of x. We do that instead of saying y inverse of x. So down here, if this was distance relation to time, I'm going to end up writing time with the relation of distance, right, rather than the inverse d of t. All right. And what specifically that does is it just changes what's the input and what the output. And again, for example, if this was my output, my input is time, my output is distance. I cannot switch those because at the end, and I've already gone through and solved this, my input is going to be distance and my output is going to be time. And although it sounds a little bit complicated, I think you'll understand it when we get down here. So let's do a couple of these, and I'll leave one for you. It says find the inverse of each quadratic function and use the inverse to solve for the application. So here we go. We have the function d of t equals 16t squared. All right, to find my inverse, I'm just going to write this as distance equals 16t squared, right? And it says d represents distance in feet. A dropped object falls in t seconds. So for this one, my input is t, and my output is distance. Alright, so if given a time, we can figure out the distance. Alright, let's go ahead and solve this. Well, I divide both sides by 16, so I get d over 16 equals t squared. Right? I divide both sides, well, I take the square root of both sides, and now I've got this. I've got t equals, well, the square root of my distance over, well, in that case, square root of 16 is 4. So I could write this as, and let's write it here, we'll say t given the input of distance is equal to the square root of distance over 4. Right? So now my input is d, and my output is t. So in this situation, if someone gives me distance, I can plug it in here and get time. If someone gives me time, I can plug it in here and get distance. So let's see what they give us. All right. Estimate how many seconds it will take a penny to drop 48 feet. So I'm going to say, all right, we'll say t of 48. We're going to plug it into this equation, our inverse equation, right? And I get the square root of 48 divided by 4. So t of 48, again, I'm inputting distance, and my output's going to be time. Let's see if Siri can answer this for me real quick. Siri, what is the square root of 48 divided by 4?
Here's what I found on the web for Siri. What is the square root of 48 divided by 4?
They gave me a website. Well, let's do our own estimation here, and I will, you have a calculator, which would be a little bit better, but I'm going to do an estimation. That's got to be, because square root of 49 is 7, so this is probably going to be about 6.9 divided by 4. Oh, again, just an estimation. 1.5 would get me up to 6. I'm going to go 1.7 seconds. If I'm a little off, please forgive me. I won't be too far off with that, but I have a calculator here, and I'm going to keep going. So, all right. So now we got a new equation. Again, our goal is just to find the inverse, plug in what they give us, and go from there. All right. So this says E of V. So I don't have electricity, energy, right? And V, let's see what it is. Gives kinetic energy. So we know E is energy in joules of an 8 kilogram object traveling at a velocity. Velocity V in meters per second. So we know what everything stands for, right? So when I write this, when I write E of V equals 4V squared, my input is velocity, right? Velocity, and my output is energy, specifically energy in joules, right? So let's go ahead and solve this. I've got E energy equals 4V squared, divide by 4. E over 4 equals V squared. If I take square root, we're going to keep this positive. You realize that should be a positive or negative, but we're going to let it, that's a positive. And I get velocity is equal to the square root of energy over 2. And I could say V of E, right? I could write that as V of E, indicating my input equals the square root of energy over 2. Those both say the same thing. And my input is energy now. And when I input energy, my output is velocity. So let's do it. Let's come over here. They're going to give us something. I'm going to move down here to kind of plug it in. Estimate the velocity required for an 8 kilogram object. That means we're using the same thing. There's no trick there. To have a kinetic energy of 60 joules. Let's do it. All right. So I'm going to say V of 60. What's the velocity when I input 60 into this equation right here? Which is going to get me what, the square root of 60 over 2. Once again, I'm just going to estimate. 64 would be 8, so I'm going to go 7.8. Again, it could be 7.9, but this is my quick estimation. If you have a calculator, use one. And that gives me about 3.9, let's see, meters per second. So I'm going to say meters per second right there. Not too bad. It has been, let's see, 7 minutes. So I'm going to let you try C. The same way we did everything else. You're just going to solve it. Remember, pi is just a number right here, so you're going to divide by pi and take square roots and then plug in what you need. And we will talk to you soon.